Welcome to Universe Scientist Stories. Tonight, we are leaving the familiar shores of our solar system to take a slow, quiet journey across our home galaxy, the Milky Way. Dim your screen, settle in, and let's drift through the stars. The Milky Way is so enormous that even the speed of light, moving at nearly 300,000 kilometers every second, requires about 100,000 years to cross its visible disk from one side to the other. Yet tonight, our path will remain within a tiny region of that vast spiral galaxy, a region astronomers call the solar neighborhood. Compared to the full scale of the Milky Way, this neighborhood is little more than a faint dust grain suspended inside an ocean of stars. And still, even this tiny local region stretches across distances so large that human intuition quietly dissolves in the attempt to imagine them. The nearest star beyond our Sun is more than 40 trillion kilometers away, separated from us by a gulf of darkness so empty that a spacecraft traveling faster than any machine humanity has ever built would still need tens of thousands of years to arrive there. Our Sun drifts through this quiet region of the galaxy at an orbital speed of roughly 220 kilometers per second. Every minute, without any sensation of motion, Earth, the Moon, and all the planets travel millions of kilometers around the galactic center simply because they are bound to the Sun, and the Sun itself is moving through the Milky Way. Yet despite this tremendous speed, one complete orbit around the galaxy takes approximately 230 million years. The last time the Sun occupied this exact region of the galaxy, dinosaurs had not yet appeared on Earth. Entire mountain ranges have risen and vanished during a single galactic year. The Sun belongs to a sparse local stellar population embedded inside the Orion Arm, sometimes called the Orion Spur. This structure is not one of the Milky Way's major spiral arms, but rather a smaller bridge-like segment located between the much larger Sagittarius Arm and Perseus Arm. From within the galaxy, these structures cannot be seen directly as graceful spirals because we are embedded inside them, surrounded by gas, dust, and stars in every direction. Humanity has spent centuries reconstructing the shape of the Milky Way indirectly, through radio observations, infrared mapping, and the slow measurement of stellar distances. The Orion Arm itself stretches for thousands of light-years, containing enormous molecular clouds where stars continue to form quietly in cold darkness. The space surrounding the Sun appears crowded in photographs of the night sky, yet reality is almost incomprehensibly empty. If the Sun were reduced to the size of a grain of sand, the nearest star would still be several kilometers away. Between stars lies the interstellar medium, a thin mixture of hydrogen atoms, helium, dust particles, magnetic fields, and wandering cosmic rays. In most regions near the Sun, the density of matter is far lower than the emptiest vacuum humans can produce in laboratories on Earth. The galaxy is not a packed city of stars pressed together side by side. It is mostly silence and separation. The nearest stellar system to Earth is Alpha Centauri, a triple-star system located about 4.37 light-years away. Two of its stars orbit each other in a configuration somewhat similar to the Sun, while the smaller companion, Proxima Centauri, drifts farther outward. Proxima is a red dwarf, faint and cool compared to the Sun, yet it is currently the closest known star to our solar system. Its dim reddish light is invisible to the naked eye from Earth despite its proximity. Red dwarfs like Proxima are the most common stars in the Milky Way, quietly burning hydrogen for trillions of years, far longer than stars like our Sun will survive. The solar neighborhood contains many stars moving together through space in loose associations known as stellar streams or moving groups. Some of these stars were born from the same giant molecular cloud hundreds of millions of years ago and still travel through the galaxy in roughly similar directions. The Sun itself may once have had thousands of stellar siblings formed alongside it in a long-dispersed star cluster over 4.5 billion years ago. Those sibling stars are now scattered throughout the Milky Way, impossible to identify with certainty among the galaxy's hundreds of billions of suns. Somewhere in the darkness may drift stars that formed beside our own Sun before Earth itself existed. Surrounding our local region is an immense cavity in the interstellar medium known as the local bubble. This structure extends for roughly 1,000 light-years across and contains unusually hot, diffuse gas. Astronomers believe the local bubble was carved by multiple ancient supernova explosions occurring millions of years ago. Massive stars once lived near this region, burning brightly and briefly before detonating in colossal explosions that swept away surrounding gas. Those explosions heated the remaining material to temperatures of millions of degrees, creating the vast low-density cavity through which the Sun now drifts silently. The local bubble is not entirely empty. Within it float thin clouds of colder gas, delicate structures suspended like faint mist inside an enormous cavern. The solar system currently resides inside one of these structures, called the local interstellar cloud. This cloud is extremely diffuse by earthly standards, yet it subtly shapes the boundary of the heliosphere, the great magnetic bubble inflated by the solar wind. As the Sun moves through the galaxy, the heliosphere changes shape slightly in response to the surrounding interstellar environment, like the wake of a ship moving through an invisible sea. The heliosphere itself extends far beyond the orbit of Pluto. The solar wind, consisting of charged particles streaming outward from the Sun, creates a protective region that shields much of the solar system from incoming galactic cosmic radiation. At the outer boundary of this region lies the heliopause, where the outward pressure of the solar wind finally weakens enough for interstellar space to push back. The Voyager spacecraft, launched in the 20th century, have now crossed this threshold into interstellar space. Their faint signals continue traveling homeward across billions of kilometers, carrying whispers from the edge of the Sun's domain. Inside the Orion Arm, stars are not evenly distributed. Some regions contain brilliant young clusters glowing blue-white with newly formed stars, while other regions remain dark and sparse. The Orion Molecular Cloud Complex, located roughly 1,300 light-years away, is one of the nearest major stellar nurseries to Earth. Within these cold clouds, gravity slowly gathers hydrogen gas into denser knots that collapse into protostars. Hidden beneath veils of dust, new suns ignite continuously throughout the Milky Way. The night sky of Earth preserves only a tiny glimpse of these immense processes unfolding across thousands of light-years. Many of the brightest stars visible from Earth belong to our broader local galactic environment. Sirius, the brightest star in Earth's night sky, lies only about 8.6 light-years away. Vega, Altair, Fomalhaut, and many other familiar stars are nearby neighbors on the scale of the galaxy. Yet even among these relatively close stars, distances remain profound. Light leaving Sirius during the final years of Earth's previous decade is only arriving now. Every glance upward into the night sky is therefore an act of looking into the past. The galaxy reveals itself not as it is now, but as it once was. The Milky Way rotates differentially, meaning stars closer to the galactic center orbit faster than stars farther away. Because of this, the Orion Arm is not a rigid structure. Over immense spans of time, stars drift relative to one another. Spiral features stretch and shear, and entire stellar neighborhoods slowly rearrange themselves. The Sun will not remain forever within the same exact local environment. Tens of millions of years from now, nearby stars will appear in entirely different positions, and Earth's night sky will become unrecognizable to future observers. Although our local region feels stable, it is permeated by invisible magnetic fields threading through the interstellar medium. These galactic magnetic fields influence the motion of charged particles, shape interstellar clouds, and help regulate star formation. The magnetic field near the Sun is extremely weak compared to anything humans experience directly, yet across galactic scales it quietly guides matter through the spiral arms. Cosmic rays accelerated by supernova explosions travel along these magnetic pathways, wandering through the Milky Way for millions of years before some eventually collide with Earth's atmosphere. The stars nearest the Sun vary enormously in size, temperature, and lifespan. Some are small red dwarfs barely larger than Jupiter, glowing faintly for trillions of years. Others are white dwarfs, dense stellar remnants no larger than Earth but containing nearly the mass of the Sun compressed into extraordinary density. A teaspoon of white dwarf matter would weigh tons on Earth. These ancient stellar corpses are common throughout the solar neighborhood, silent remnants of stars that exhausted their nuclear fuel long before human civilization appeared. Brown dwarfs also drift through the local region in great numbers. These objects occupy the boundary between stars and planets. They are too massive to be planets, yet too small to sustain long-term hydrogen fusion in their cores. As a result, they emit only faint heat and dim infrared light, gradually cooling over billions of years. Many brown dwarfs remain undiscovered because they are so dark and difficult to detect against the cold background of space. The solar neighborhood may contain enormous populations of these wandering failed stars hidden within the darkness between brighter suns. The Orion Arm contains vast reservoirs of cold molecular hydrogen, the raw material from which stars are born. In the coldest regions, temperatures fall to only a few degrees above absolute zero. Under such conditions, atoms move slowly enough for molecules to form, and dense clouds become opaque to visible light. Infrared telescopes reveal intricate structures within these clouds, including pillars, filaments, and collapsing cores. Star formation is not explosive on human timescales. It unfolds gradually over millions of years, as gravity patiently shapes the architecture of future solar systems. Near the Sun, astronomers have identified a structure called the Gould Belt, a partial ring of young stars and star-forming regions tilted relative to the plane of the Milky Way. This structure spans several thousand light-years and includes many familiar constellations visible from Earth, including Orion, Scorpius, and Perseus. The origin of the Gould Belt remains uncertain, though it may have formed from ancient collisions between interstellar clouds or from a burst of star formation triggered by past galactic events. It represents another reminder that our local region carries the long echoes of ancient cosmic processes. The local bubble itself appears connected to neighboring cavities in the interstellar medium, forming a network of enormous hollow regions sculpted by generations of supernova explosions. These superbubbles overlap and expand through the galaxy over millions of years. The Milky Way is therefore not a smooth ocean of gas, but a constantly changing environment shaped by stellar birth and stellar death. Massive stars live briefly, explode violently, and in doing so create the conditions for future generations of stars and planets to emerge. The atoms inside Earth's oceans, mountains, and living creatures were forged long ago inside such stars. Our Sun is currently located slightly above the galactic plane, the dense central layer where most stars in the Milky Way reside. It oscillates slowly up and down through this plane over tens of millions of years as it orbits the galaxy. During these oscillations, the solar system encounters changing galactic environments with varying densities of gas, dust, and nearby stars. Some researchers have explored whether these long galactic cycles may subtly influence Earth's climate or comet activity, though the evidence remains uncertain. Still, the motion reminds us that the solar system is not fixed within the galaxy. It is continuously traveling through changing regions of space. Within the local neighborhood are stars that move at extraordinary speeds relative to the Sun. Some may have been accelerated long ago through gravitational interactions or supernova explosions. Barnard's star, for example, moves rapidly across Earth's sky compared to more distant stars because of its proximity and velocity. Over thousands of years, its position shifts noticeably against the background constellations. The stars above humanity therefore do not form eternal patterns. Constellations are temporary arrangements created by perspective and time. The interstellar dust within the Orion Arm plays a profound role in shaping what humanity can see. Dust grains smaller than smoke particles absorb and scatter visible light, hiding large portions of the galaxy from direct observation. The bright band of the Milky Way stretching across Earth's sky is crossed by dark lanes where dense clouds block starlight from more distant regions. Infrared and radio telescopes have gradually allowed astronomers to peer through these veils, revealing hidden star clusters, molecular clouds, and the distant structure of the galactic disk beyond visible sight. The solar neighborhood is also home to rogue planets, worlds that drift freely through interstellar space without orbiting any star. Some were likely ejected from young planetary systems during gravitational chaos billions of years ago. Others may have formed independently within collapsing gas clouds. These isolated planets wander through the darkness of the Milky Way almost completely invisible, illuminated only faintly by residual internal heat. In the immense emptiness between stars, there may exist countless frozen worlds traveling alone through eternal night. Even in our relatively calm local region, supernova explosions occasionally occur on astronomical timescales. Evidence found in deep-sea sediments on Earth suggests that nearby supernovae exploded within a few hundred light-years of the solar system several million years ago. Radioactive isotopes produced in those explosions eventually settled onto Earth's oceans. Although distant enough to avoid catastrophic damage, such events remind us that the galaxy is not entirely quiet. Stellar death continuously reshapes the interstellar environment surrounding the Sun. The Orion Arm contains open star clusters, loose collections of stars born together from the same cloud. Over time, these clusters gradually disperse as gravitational interactions pull them apart. The Pleiades cluster, visible to the naked eye, is one nearby example of such a youthful stellar family. Its bright blue stars are only around 100 million years old, extremely young compared to the Sun. Eventually, the cluster will dissolve completely, its stars spreading across the galaxy until their shared origin becomes almost impossible to trace. Far beyond the visible stars of the solar neighborhood lies an unseen component of the Milky Way known as dark matter. Although invisible, Dark matter exerts gravitational influence throughout the galaxy and helps hold it together. Measurements of stellar motion reveal that the visible matter in the Milky Way is not sufficient to explain how rapidly stars orbit the galactic center. The solar system itself moves through a vast halo of this mysterious substance, though its true nature remains unknown. Even within our familiar galactic neighborhood, most of the mass surrounding us cannot be directly seen. At night, when Earth's skies are dark enough for the Milky Way to appear clearly overhead, the faint river of light crossing the heavens is actually the combined glow of countless distant stars within the galactic disk. Human eyes cannot separate them individually. The Orion Arm contributes only a small fraction of that glow, while enormous populations of stars farther inward toward the galactic center create the brighter regions of the Milky Way band. Looking upward from Earth is therefore like standing deep inside a forest at night, seeing countless distant lights through layers of obscuring mist and darkness. And so, within this small corner of the Milky Way, the sun continues its quiet journey. Around it drift neighboring stars, cold clouds of hydrogen, invisible magnetic fields, ancient supernova remnants, and wandering planets lost between suns. The local bubble carries the scars of long-dead stars. The Orion Arm stretches onward through thousands of light-years of darkness and faint light. And beyond it all, the wider galaxy turns slowly in silence, carrying every star, every planet, and every living thing together around a distant center none of us can see from here. In the immense calm of local space, even our nearest stellar neighbors remain unimaginably far away, separated by oceans of darkness so vast that human history itself becomes smaller than a passing moment within the long drifting structure of the Milky Way. Farther inward along the galactic disk, beyond the quieter structure of the Orion Arm, the Milky Way begins to gather itself into denser rivers of gas and stars, where the great spiral arms emerge from darkness like slow-moving currents inside an immense luminous sea. The spiral arms of the Milky Way are not solid structures fixed permanently in place. They are regions of enhanced density, waves moving gradually through the galactic disk, compressing gas clouds as stars and interstellar matter drift through them. In some ways, they resemble galactic traffic patterns, where material slows and gathers temporarily before continuing onward in its orbit around the center of the galaxy. Because of this compression, spiral arms become crowded with molecular clouds, newborn stars, and glowing nebulae. They are the principal regions where stellar birth occurs on the largest scales. The Perseus Arm and the Scutum Centaurus Arm contain some of the most active and massive star-forming regions in the Milky Way, stretching across tens of thousands of light-years through the rotating body of the galaxy. The Perseus Arm lies farther outward from the galactic center than the Sun's position. It is one of the Milky Way's major spiral arms, broad and heavily populated with young stars, open clusters, and giant clouds of molecular hydrogen. Radio observations reveal its structure extending through large portions of the galactic disk, though dust prevents direct optical observation across its full length. The stars forming inside the Perseus Arm are often hot, blue, and short-lived, illuminating nearby clouds with intense ultraviolet radiation. These young stars mark the locations where cold gas has recently collapsed under gravity. Across the arm, entire stellar generations emerge continuously from dark clouds hidden behind curtains of dust. Closer toward the galactic center lies the immense Scutum Centaurus Arm, one of the Milky Way's dominant spiral features. This arm contains extraordinary concentrations of gas and dust, including some of the galaxy's largest known molecular cloud complexes. In certain regions, Star formation proceeds on scales difficult to fully imagine, producing clusters containing thousands of stars. Massive stars born there burn with such intensity that they reshape their environments within only a few million years. Their radiation carves cavities into surrounding clouds, while stellar winds drive shockwaves through the gas. The arm itself glows strongly in infrared wavelengths because warm dust permeates the region in enormous quantities. Inside these spiral arms, the darkness between stars is no longer nearly empty. Giant molecular clouds drift through the galaxy like cold continents suspended in space. Some span hundreds of light years and contain enough material to create millions of stars like the Sun. Despite their enormous mass, these clouds are extremely diffuse compared to Earth's atmosphere. A human standing inside one would scarcely notice it at all, except for the obscuring darkness. The clouds appear opaque from a distance because even tiny amounts of dust, spread across immense distances, block visible starlight very effectively. Entire stellar nurseries remain hidden within these cold interiors, invisible to ordinary telescopes. The temperatures inside molecular clouds are remarkably low, often only 10 to 20 degrees above absolute zero. At such temperatures, atoms move slowly enough to form molecules, especially molecular hydrogen, which becomes the dominant ingredient in star-forming regions. Tiny grains of silicate dust and carbon-rich particles drift among the gas, coated in thin layers of frozen water, ammonia, methane, and carbon monoxide. These microscopic particles help cool the clouds by radiating energy into space. Without such cooling, gravity would struggle to compress the gas efficiently enough for stars to form. In this way, even the smallest dust grains participate in shaping the future architecture of galaxies. Gravity inside giant molecular clouds acts constantly but slowly. For millions of years, turbulence, magnetic fields, and gas pressure resist collapse, creating a balance between inward pull and outward motion. Yet eventually, some regions become slightly denser than their surroundings. Once enough matter gathers together, gravity strengthens further, drawing in additional gas. These denser regions are called molecular cloud cores, and they represent the earliest visible stages of stellar birth. Within them, collapse begins quietly in complete darkness. No star yet shines. Only cold gas drifts inward through silence beneath layers of obscuring dust. As cloud cores contract, gravitational energy converts gradually into heat. Temperatures within the collapsing material begin to rise, though the outer cloud may remain extremely cold. The collapsing region spins faster as it shrinks, conserving angular momentum in much the same way a spinning skater rotates more rapidly when pulling inward. This rotation causes material to flatten into a dense disk surrounding the growing protostar at the center. Nearly every star in the galaxy likely forms within such rotating disks. From these disks, planets, moons, asteroids, and comets may eventually emerge over immense spans of time. The earliest stage of a forming star is deeply hidden inside its natal cloud. Protostars emit mostly infrared radiation because surrounding dust absorbs visible light and re-radiates the energy at longer wavelengths. Infrared telescopes have therefore transformed humanity's understanding of star formation by allowing astronomers to peer inside these dark stellar nurseries. Observations from space observatories reveal thousands of infant stars embedded within clouds once thought to be empty darkness. The Milky Way contains vast populations of these unseen protostars quietly growing within cold molecular regions spread across the spiral arms. One of the nearest and most studied stellar nurseries is the Orion Nebula, located roughly 1,300 light-years from Earth within the Orion Molecular Cloud Complex. To the naked eye, it appears as a faint glowing patch in the sword of the constellation Orion. Yet through telescopes, the nebula reveals itself as a vast cavity of ionized gas illuminated by newly formed stars near its center. The cloud surrounding the nebula contains enough material to create many thousands more stars in the future. Within its interior, astronomers observe disks around young stars, jets of gas launched from protostars, and intricate structures shaped by radiation and turbulence. The bright glow of the Orion Nebula originates primarily from hydrogen atoms energized by ultraviolet radiation emitted by hot young stars. These massive stars formed recently within the cloud and now flood the surrounding gas with energetic photons. Electrons stripped from hydrogen atoms eventually recombine and emit visible light, producing the nebula's characteristic reddish and pink coloration. Such emission nebulae are temporary structures on cosmic timescales. Over millions of years, stellar winds and radiation disperse the gas, gradually exposing the young cluster hidden within the cloud. The nebula fades, while its newborn stars continue orbiting the galaxy independently. Within the Orion Nebula are small dark structures called Bok globules, compact clouds of dust and gas where additional stars may still be forming. These globules appear as silhouettes against the brighter glowing background of ionized hydrogen. They are among the coldest and densest structures in star-forming regions, preserving pockets of darkness even amid intense radiation nearby. Inside them, gravity continues gathering matter toward unseen protostars. Some may eventually form stars smaller than the Sun, while others might create entire planetary systems hidden for millions of years before their surrounding dust finally clears away. The Carina Nebula, located several thousand light-years away within the Carina-Sagittarius region of the Milky Way, is vastly larger and more energetic than Orion. It spans hundreds of light-years and contains enormous populations of massive young stars. Ultraviolet radiation and stellar winds from these stars sculpt towering pillars, cavities, and ridges within the surrounding molecular clouds. The nebula shines brilliantly across visible and infrared wavelengths, revealing a chaotic landscape of stellar birth and destruction unfolding simultaneously. Carina represents one of the galaxy's most active nearby star-forming complexes, where immense amounts of gas continue collapsing into new stars even as older massive stars destabilize the surrounding environment. Among the stars inside the Carina Nebula is Eta Carinii, one of the most luminous and massive stellar systems known in the Milky Way. This unstable star emits millions of times more energy than the Sun and ejects enormous quantities of matter into surrounding space. Massive stars like Eta Carinii profoundly influence stellar nurseries because their radiation and winds compress nearby gas while dispersing other regions entirely. They may trigger additional star formation by driving shockwaves into molecular clouds, creating new dense cores that eventually collapse under gravity. In this way, one generation of stars can influence the birth of the next. Star formation efficiency inside molecular clouds is surprisingly low. Even giant clouds containing enough material for millions of stars convert only a small percentage of their gas into stellar objects before feedback processes disrupt the cloud. Radiation pressure, stellar winds, and supernova explosions gradually disperse the remaining gas back into the interstellar medium. Much of the cloud therefore returns to diffuse galactic space rather than becoming part of stars. The Milky Way maintains an ongoing cycle in which gas gathers into clouds, forms stars, disperses again, and later becomes incorporated into future generations of stellar nurseries. Cosmic dust, though accounting for only a small fraction of the mass inside molecular clouds, plays an essential role in galactic chemistry. The surfaces of dust grains allow atoms to combine into molecules more efficiently than they could within empty space alone. Water molecules, simple organic compounds, and other complex chemicals form on these cold surfaces within dark clouds. Some of the chemical ingredients necessary for planets and possibly life itself therefore begin assembling long before stars fully ignite. The chemistry of future solar systems starts quietly inside frozen grains drifting through ancient clouds of interstellar darkness. As protostars grow, powerful jets often erupt outward from their poles at hundreds of kilometers per second. These bipolar outflows arise because magnetic fields channel some of the infalling material away from the forming star rather than allowing all of it to accrete inward. The jets carve narrow tunnels through surrounding gas and can extend for light years into space. Where they collide with the interstellar medium, glowing shock fronts called big haro objects appear. These structures provide visible evidence of ongoing star formation hidden within otherwise opaque molecular regions. The balance between gravity and pressure determines whether a cloud core continues collapsing into a star. When enough mass accumulates, temperatures and pressures inside the core eventually become extreme enough for nuclear fusion to begin. Hydrogen nuclei fuse into helium, releasing vast quantities of energy. At this moment, a true star is born. Fusion creates outward pressure that halts further gravitational collapse, establishing a long-lasting equilibrium that may persist for billions of years. The ignition of fusion transforms a dark protostar into a stable luminous object capable of illuminating surrounding space. Most stars in the Milky Way do not form alone. Molecular clouds often fragment into multiple collapsing regions, producing binary stars, triple systems, or entire clusters. The Sun itself may once have formed within a crowded stellar nursery alongside thousands of neighboring stars. In dense clusters, gravitational interactions between young stars can alter planetary systems, eject planets into interstellar space, or redistribute material within protoplanetary disks. The environment surrounding a newborn star therefore strongly influences the long-term evolution of any planets that eventually emerge around it. Massive stars form more rapidly than smaller stars because their stronger gravity gathers material at higher rates. Some may reach full size in only a few 100,000 years, extremely quickly by astronomical standards. Yet these stars live brief lives. Their intense luminosities consume nuclear fuel rapidly, limiting their lifespans to only millions of years. Smaller stars like red dwarfs evolve far more slowly and may survive for trillions of years. The Milky Way's spiral arms therefore shine brightly with young massive stars, even though such stars are relatively rare compared to smaller, dimmer suns. Dust within stellar nurseries shapes light in subtle ways. Shorter blue wavelengths scatter more efficiently than red wavelengths, causing distant stars viewed through dusty regions to appear redder than they truly are. Astronomers call this effect interstellar reddening. By measuring how starlight changes as it passes through clouds, researchers can estimate the density and composition of interstellar dust. Such measurements reveal that dust grains contain silicates, carbon compounds, and traces of heavier elements forged within earlier generations of stars. Every grain drifting through a molecular cloud carries the history of ancient stellar processes. The Eagle Nebula, another active star-forming region within the Milky Way, contains towering structures famously known as the Pillars of Creation. These immense columns of cold gas and dust extend for several light-years and shelter newly forming stars inside their dense interiors. Ultraviolet radiation from nearby massive stars slowly erodes the pillars from the outside, sculpting them into elongated forms pointing away from the energetic cluster. Although they appear solid in photographs, the pillars are tenuous clouds suspended in near vacuum, shaped continuously by radiation and stellar winds moving through the surrounding nebula. Within giant molecular clouds, turbulence creates chaotic motions that influence where stars can form. Supersonic flows of gas collide and compress material into filaments spanning dozens of light-years. Modern observations show that filamentary structures are nearly universal in star-forming clouds. Stars often emerge where multiple filaments intersect, producing dense knots capable of gravitational collapse. These vast thread-like structures drift slowly through darkness, channeling matter across enormous distances inside the spiral arms of the Milky Way. The architecture of stellar nurseries therefore resembles an intricate cosmic web woven from cold hydrogen and dust. Not all collapsing cloud cores become stars. Some gather insufficient mass to ignite hydrogen fusion and instead form brown dwarfs, objects occupying the boundary between planets and stars. Others may fragment repeatedly during collapse, creating unstable systems that disperse before star formation fully completes. The outcome depends on complex interactions among gravity, magnetic fields, turbulence, and radiation. Stellar birth is therefore not a perfectly orderly process. Inside giant molecular clouds, countless invisible events unfold simultaneously, each following slightly different paths through the long evolution of interstellar matter. The spiral arms themselves help sustain star formation because their density waves compress gas clouds as material orbits through them. When diffuse interstellar gas enters a spiral arm region, pressure increases and molecular clouds grow denser. This enhanced density encourages gravitational collapse and the formation of new stars. After stars emerge and continue orbiting the galaxy, they eventually drift away from the spiral arm where they formed. The arms are therefore continuously renewed by fresh generations of stars appearing within compressed gas. They are not permanent collections of the same objects, but evolving patterns moving through the galactic disk over immense spans of time. Supernova explosions inside star-forming regions contribute heavy elements back into surrounding clouds. Elements such as oxygen, carbon, silicon, calcium, and iron are synthesized inside stars and released into space during stellar death. These materials later become incorporated into future generations of stars and planets. The iron within human blood and the calcium within human bones were forged inside ancient stars long before the Sun existed. Giant molecular clouds therefore contain the accumulated chemical history of countless earlier stellar generations, enriched slowly across billions of years of galactic evolution. Infrared observations of the Milky Way reveal that many stellar nurseries remain entirely hidden behind thick curtains of dust when viewed in visible light. Some of the galaxy's most active star-forming regions were discovered only recently because optical telescopes could not penetrate the obscuring clouds. Infrared radiation passes more easily through dust, allowing astronomers to map embedded clusters and protostars deep within molecular complexes. The true appearance of the Milky Way is therefore very different from what human eyes alone can perceive. Beneath the visible stars lies an unseen galaxy of cold clouds, newborn suns, and glowing dust structures extending across the spiral arms in silence. and deeper still within those immense spiral currents, where cold hydrogen drifts through darkness and dust slowly gathers around invisible centers of gravity. The galaxy continues its endless work of creation, building new stars grain by grain, cloud by cloud, across distances so vast that entire stellar civilizations could rise and disappear while a single molecular cloud quietly collapses toward the first faint ignition of light. Toward the inner regions of the Milky Way, the darkness between stars gradually begins to fade beneath an increasing concentration of ancient light, and the calm emptiness of the outer spiral arms gives way to the crowded brilliance surrounding the galactic core. The central region of the Milky Way is known as the galactic bulge, a vast rounded concentration of stars occupying the inner thousands of light-years around the galaxy's center. Unlike the thin spiral arms surrounding it, the bulge rises above and below the galactic plane in a swollen distribution shaped somewhat like a flattened sphere. Billions of stars drift through this region in densely packed orbits governed by the enormous gravitational mass gathered near the core. From Earth, much of the bulge remains hidden behind thick curtains of dust lying within the galactic disk, yet infrared telescopes reveal an immense golden glow beneath the obscuring clouds. As one approaches the galactic center in imagination, the number of visible stars would increase dramatically. In the solar neighborhood, nearby stars are separated by several light-years on average, leaving enormous regions of empty space between them. Near the core, however, stellar densities become far greater. In some regions of the inner bulge, stars may lie only fractions of a light-year apart. The night sky of a planet orbiting a stable star near the galactic center could appear permanently crowded with brilliant suns shining in every direction. Darkness itself would become difficult to find amid the overwhelming concentration of starlight. Many of the stars inhabiting the galactic bulge are extremely old. Astronomers estimate that large populations there formed more than 10 billion years ago, during the early history of the Milky Way. These ancient stars preserve clues about the galaxy's formation because they contain fewer heavy elements than younger stars born later in galactic history. In astronomy, all elements heavier than hydrogen and helium are called metals, even substances such as oxygen and carbon. Early generations of stars formed before repeated supernova explosions enriched the galaxy with large amounts of these heavier materials. The ancient stars near the bulge therefore act as living records from the Milky Way's distant past. The shape of the bulge itself appears more complex than astronomers once believed. Infrared surveys indicate that the central region contains a long bar-shaped structure extending outward from the nucleus of the galaxy. This stellar bar channels gas inward through gravitational interactions, helping feed star formation near the center. Similar bars are observed in many spiral galaxies throughout the universe. The Milky Way, viewed from far beyond its disk, would likely appear as a barred spiral galaxy with sweeping arms emerging from the ends of this elongated central structure. Yet from Earth, embedded within the disk, humanity reconstructs this architecture indirectly through careful mapping across many wavelengths of light. Closer to the center, interstellar gas clouds become warmer, denser, and more turbulent than those found within the quieter outer arms. Powerful magnetic fields thread through the inner galaxy, while supernova explosions and intense stellar winds constantly stir the surrounding medium. Giant molecular clouds orbit through these crowded environments under enormous gravitational stress. Some clouds near the core contain millions of solar masses of material compressed into relatively compact regions. Inside them, star formation can proceed rapidly, producing dense clusters filled with massive luminous stars whose radiation floods surrounding space with energy. The galactic bulge shines strongly with the light of red giant stars. These aging stars represent a later stage in stellar evolution after hydrogen fusion in their cores has largely ceased. As their internal structure changes, their outer layers expand enormously and cool slightly, causing them to glow with deep orange and reddish hues. Some red giants become hundreds of times larger than the Sun. If one replaced our Sun at the center of the solar system, its outer atmosphere might extend beyond the orbit of Earth. Across the bulge, billions of such stars contribute to the warm golden coloration seen in infrared observations of the galactic center. Red giants evolve slowly over immense spans of time. Inside their interiors, fusion continues in shells surrounding dense cores composed mostly of helium or heavier elements. These stars gently shed material into space through slow stellar winds, enriching the interstellar medium with carbon, nitrogen, oxygen, and dust grains formed in their extended atmospheres. Much of the material necessary for future planets and future living organisms originates from stars passing through these late evolutionary stages. The galaxy recycles stellar matter continuously, allowing atoms forged inside ancient stars to become part of entirely new generations of suns and worlds billions of years later. Near the innermost regions of the Milky Way, the brightness of the stellar population would overwhelm the familiar darkness of Earth's night sky. On Earth, the sky between stars appears mostly black because our solar system resides in a relatively sparse region of the galactic disk. Near the center, however, the combined light of countless nearby stars would create a persistent luminous background. The galactic core, if directly visible without dust obstruction, would appear far brighter than the moon across large portions of the sky. The central regions of the Milky Way contain such extraordinary numbers of stars that their collective glow dominates the inner galaxy. Despite this brilliance, enormous clouds of dust still permeate the core region. Visible light from the galactic center is heavily absorbed before reaching Earth, forcing astronomers to rely on infrared, radio, and X-ray observations to study the nucleus directly. Dust grains drifting through the inner galaxy scatter and absorb shorter wavelengths efficiently, concealing the core behind dark lanes when viewed optically. Infrared radiation penetrates these clouds more effectively, revealing dense stellar populations hidden beneath the obscuration. Modern infrared observatories have therefore transformed understanding of the galactic bulge and the structures surrounding the center of the Milky Way. Among the oldest objects associated with the Milky Way are globular clusters, enormous spherical collections of ancient stars orbiting far above and below the galactic disk. More than 150 known globular clusters surround the Milky Way, forming part of its extended halo population. Each cluster may contain hundreds of thousands or even millions of stars packed into relatively compact volumes only a few dozen light-years across. Toward the centers of these clusters, stellar densities become so extreme that stars may pass comparatively close to one another over astronomical timescales, creating environments very different from the quiet isolation surrounding the Sun. Globular clusters are astonishingly ancient. Many formed more than 12 billion years ago, meaning they originated when the universe itself was still very young. Their stars contain extremely low abundances of heavy elements, indicating that they formed before repeated cycles of stellar evolution enriched galaxies with heavier chemical material. Some globular clusters may predate the assembly of the Milky Way's present spiral structure entirely. They drift through extended orbits around the galaxy like surviving relics from the early universe, preserving conditions that existed long before Earth or the Sun came into existence. Seen from within, a globular cluster would present a spectacular sky unlike anything visible from Earth. Stars would crowd the heavens in every direction, many appearing vastly brighter than any star in Earth's current night sky. The central regions of some clusters contain stars separated by only weeks or months of light travel time rather than years. Yet despite this apparent crowding, direct stellar collisions remain relatively rare because stars themselves are extremely small compared to the distances between them. Even inside these dense stellar systems, space remains mostly empty, though far less empty than the regions surrounding our own Sunday. The stars inhabiting globular clusters are generally smaller and older than the massive blue stars dominating active spiral arms. Most hot, short-lived stars inside these clusters died billions of years ago, leaving behind populations dominated by long-lived red and yellow stars. As a result, globular clusters often appear warm and golden in color. Their ancient stellar populations evolve slowly, creating an atmosphere of quiet stability compared to the turbulent star-forming regions of the spiral arms. Many clusters have orbited the Milky Way repeatedly for billions of years, while entire generations of stars formed and vanished elsewhere in the galaxy. The gravitational pull within the inner galaxy shapes the orbits of stars in complex ways. Unlike stars in the outer disk, which move along relatively orderly circular paths around the galactic center, stars within the bulge follow more varied and elongated trajectories. Some orbit through the central regions in tilted paths influenced by the galaxy's bar structure and overall mass distribution. Over immense periods, these countless stellar orbits create the smooth, glowing appearance of the bulge when viewed from afar. Beneath that calm luminosity lies a ceaseless motion involving billions of stars traveling through deep gravitational currents. The total mass concentrated near the galactic center is enormous. Billions of stars, immense molecular clouds, dark matter, and the central supermassive black hole together generate gravitational forces that dominate the inner Milky Way. Stars near the core orbit at tremendous velocities as they respond to this concentrated mass. Astronomers measure these motions carefully to infer the distribution of matter hidden within the central regions. The faster stars move, the greater the gravity required to hold them in orbit. Through such measurements, researchers have gradually revealed the extraordinary environment surrounding the heart of the galaxy. The galactic bulge also contains large populations of variable stars whose brightness changes rhythmically over time. Certain types, such as RR Lyrae stars, are especially valuable to astronomers because their intrinsic luminosities are well understood. By comparing how bright these stars appear from Earth to how bright they truly are, astronomers can estimate distances across the bulge and halo. These ancient pulsating stars therefore serve as cosmic measuring tools, helping map the three-dimensional structure of the Milky Way. Their steady cycles of brightening and dimming continue quietly amid the crowded stellar populations surrounding the core. Some of the most luminous stars near the galactic center belong to rare populations of supergiants and hypergiants. These enormous stars burn nuclear fuel at extraordinary rates and emit vast amounts of radiation. Their surfaces may be unstable, ejecting shells of gas into surrounding space. Though comparatively rare, their brilliance allows them to stand out even within the crowded inner galaxy. Massive stars near the core contribute strongly to the energy balance of the interstellar medium through stellar winds, ultraviolet radiation, and eventual supernova explosions. Their lives are brief, but their influence spreads across surrounding molecular clouds and neighboring star clusters. The inner Milky Way contains giant star clusters unlike those found near the Sun. Some clusters near the core are so massive and compact that they rival small galaxies in stellar density. Within these crowded systems, gravitational interactions between stars become increasingly significant. Binary stars may exchange companions, compact stellar remnants may capture nearby stars, and rare collisions can occasionally occur. Such extreme environments provide astronomers with opportunities to study stellar evolution under conditions far different from those of the quieter solar neighborhood. The inner galaxy therefore acts as a natural laboratory for understanding dense stellar systems. Interstellar dust near the galactic center absorbs visible light so effectively that the nucleus remained mysterious for most of human history. Early observers looking toward the constellation Sagittarius saw only dark rifts and crowded starfields within the Milky Way band. Only in the 20th century did radio astronomy begin revealing powerful emissions emerging from the hidden center. Later infrared observations uncovered dense stellar populations previously concealed behind dust clouds. Humanity's understanding of the galactic core expanded slowly as technology learned to observe wavelengths capable of penetrating the obscuring material lying between Earth and the inner galaxy. The bulge region rotates differently from the thin disk surrounding it. Rather than behaving like a flat rotating layer alone, the bulge exhibits more complex internal motions shaped by its three-dimensional structure. Stars within the bulge move through overlapping orbital families influenced by the galaxy's bar and central gravitational potential. Simulations suggest that the bulge may have evolved gradually from instabilities within the ancient galactic disk itself, rather than forming entirely through violent mergers. The central Milky Way therefore preserves evidence of long dynamical processes unfolding over billions of years within the evolving structure of the galaxy. Ancient stars near the center often possess highly elliptical orbits carrying them repeatedly through the dense inner regions of the Milky Way. During each orbit, they experience changing gravitational environments and pass through crowded stellar fields rich with gas and radiation. Some of these stars may have formed during the earliest phases of galactic assembly, surviving nearly unchanged since shortly after the Milky Way itself began to take shape. Their continued existence provides direct observational links to the conditions prevailing in the young universe more than 10 billion years ago. The chemical composition of stars within the bulge varies considerably. Some populations contain relatively high abundances of heavy elements, indicating later generations of star formation enriched by earlier stellar deaths. Others remain metal-poor and ancient. By studying these chemical patterns, astronomers reconstruct the evolutionary history of the inner galaxy. Spectroscopy reveals the fingerprints of elements within stellar atmospheres, allowing researchers to determine how different populations formed and evolved over time. The galactic bulge, therefore, contains a layered record of star formation stretching across most of cosmic history. Globular clusters orbiting the Milky Way occasionally pass through the galactic disk during their long journeys around the halo. These passages subject them to gravitational stresses capable of slowly stripping stars away from the clusters. Over billions of years, tidal interactions gradually erode some clusters, leaving streams of stars stretched across the galaxy. Astronomers detect these stellar streams as faint elongated structures tracing the paths of disrupted systems. Even the ancient globular clusters are not perfectly permanent. Gravity reshapes them continuously across immense spans of time as they orbit through the Milky Way's gravitational field. Near the center of the galaxy, stellar remnants become increasingly common. White dwarfs, neutron stars, and stellar mass black holes accumulate in dense populations because massive stars evolve and die relatively quickly in the crowded inner regions. Some of these compact remnants exist within binary systems where matter flows from one star onto another, producing powerful X-ray emissions. Others drift silently through the stellar background, almost impossible to detect directly. The galactic core, therefore, contains not only immense concentrations of living stars, but also countless remnants left behind by earlier stellar generations. The light emerging from the central regions of the Milky Way has traveled through space for tens of thousands of years before reaching Earth. Photons leaving stars near the core began their journey long before human civilization developed agriculture or built cities. Some of the ancient globular clusters surrounding the galaxy emitted the light now reaching Earth before the continents occupied their current positions. Looking toward the galactic center, therefore, means observing deep layers of time as well as distance. The Milky Way becomes not only a structure in space, but also a vast archive preserving the long history of stellar evolution. And within that crowded brilliance surrounding the hidden nucleus of the galaxy, where ancient stars drift through overlapping tides of gravity and globular clusters continue their slow orbits through the halo of the Milky Way, the immense central regions glow on in patient silence, filling the darkness with the accumulated light of billions upon billions of suns born long before the Earth itself first formed from dust. Far above the plane of the Milky Way, many globular clusters travel through enormous looping orbits that carry them tens of thousands of light-years from the galactic center before gravity slowly draws them inward again. These ancient systems are not confined to the bright disk where most visible stars reside. Instead, they occupy the galactic halo, a vast spherical region surrounding the Milky Way on all sides. Some clusters may have originated within smaller dwarf galaxies later absorbed by the growing Milky Way during its early evolution. Their unusual motions and chemical compositions preserve evidence of these long-vanished galactic mergers, allowing astronomers to reconstruct fragments of the Milky Way's ancient assembly history from the surviving paths of these stellar relics. Inside dense globular clusters, stars move under the constant influence of nearby gravitational encounters. Over immense timescales, heavier stars and stellar remnants gradually sink toward the cluster's center through a process called mass segregation. Lighter stars drift outward into wider orbits, while compact remnants accumulate near the core. This slow internal rearrangement changes the structure of clusters continuously across billions of years. In some clusters, central densities become extraordinarily high, with thousands of stars occupying regions only a few light-years across. Yet even amid such density, the motions remain graceful and quiet, governed by the steady mathematics of gravity acting patiently over cosmic time rather than by sudden violent collisions. The galactic bulge also contains large populations of red clump stars, aging suns that have entered stable phases of helium fusion within their cores. Because these stars possess relatively consistent luminosities, astronomers use them to map the shape of the bulge and the inner bar structure of the Milky Way. Surveys measuring millions of red clump stars reveal that the bulge possesses an elongated peanut-like geometry extending above and below the galactic plane. This unusual shape likely emerged gradually through dynamical instabilities within the rotating disk billions of years ago. The inner galaxy therefore continues to evolve even after its initial formation, reshaping its structure slowly through the collective gravitational behavior of countless orbiting stars. Within the crowded central regions, gravitational tides from the galaxy itself influence the survival of star clusters. Clusters passing too close to the nucleus may gradually lose outer stars to the surrounding stellar background. Some eventually dissolve entirely, their former members dispersing into the bulge population until their shared origins become impossible to recognize. The stars of destroyed clusters continue orbiting the galaxy independently, blending into the immense stellar currents surrounding the core. In this way, the bulge slowly grows and changes through the absorption of smaller stellar systems over billions of years. The central Milky Way therefore acts both as a birthplace for stars and as a graveyard where ancient structures are slowly dismantled by gravity. Many red giant stars near the core pulsate gently as their outer layers expand and contract over regular cycles. These pulsations alter the star's brightness and temperature in predictable patterns. Mira variables, for example, can brighten and fade dramatically over periods lasting many months. During these late evolutionary stages, stars lose substantial amounts of mass into surrounding space through slow stellar winds enriched with heavy elements and dust. Infrared observations reveal shells of material drifting outward from aging giants throughout the bulge. The dust released by these stars eventually becomes incorporated into future molecular clouds, contributing raw material for later generations of stars and planets forming elsewhere within the Milky Way. The concentration of stars near the galactic center also increases the frequency of gravitational lensing events. When one star passes directly between Earth and a more distant background star, its gravity bends and magnifies the light from the distant object. Astronomers monitoring dense star fields within the bulge observe thousands of these temporary brightenings. Such microlensing events allow researchers to detect otherwise invisible objects including faint stars, brown dwarfs, and even planets drifting through the inner galaxy. Gravity itself becomes a natural telescope in these crowded regions, briefly focusing distant starlight as objects move across the observer's line of sight through the deep stellar fields surrounding the core. Viewed from far outside the Milky Way, the galactic bulge would likely appear as a bright golden heart embedded within the softer blue glow of the spiral arms. The arms would contain younger populations dominated by hot massive stars, while the bulge would radiate primarily from older, cooler stellar populations accumulated over immense spans of time. This contrast between youthful spiral structure and ancient central concentration appears in many large spiral galaxies throughout the universe. The Milky Way therefore shares common structural features with countless other galaxies spread across cosmic space. Yet from within our embedded position inside the disk, humanity experiences this immense galactic architecture only indirectly, piecing together the anatomy of our home galaxy through patient observation beneath the quiet movement of ancient light. The radiation environment near the galactic center differs greatly from the calmer conditions surrounding the sun-massive stars, supernova remnants, energetic magnetic fields, and dense concentrations of stellar remnants together generate intense streams of high-energy particles and radiation. Gas clouds moving through the inner galaxy are exposed to stronger heating and turbulence, while stellar winds from crowded populations continuously reshape nearby interstellar material. Even so, gravity maintains broad order within this energetic environment, guiding billions of stars through repeating orbits around the hidden nucleus. Amid the brilliance and radiation, the same physical laws operating within quiet molecular clouds of the outer disk continue governing the behavior of matter near the core. Hydrogen still fuses into helium inside stellar interiors. Dust still drifts through interstellar space. Ancient stars still age gradually beneath the immense gravitational architecture of the Milky Way. Astronomers studying the bulge have discovered that many stars there move together in coherent streams left behind by long-ago mergers and disrupted clusters. These stellar populations preserve faint dynamical memories of events that occurred billions of years in the past when the Milky Way absorbed smaller neighboring galaxies. Computer simulations suggest that the early galaxy grew through repeated mergers, gradually accumulating mass and reshaping its structure over cosmic time. Some of the oldest stars ever observed within the Milky Way may therefore have originated outside the galaxy entirely before becoming incorporated into the bulge and halo. Their continued presence reveals that galaxies are not static, isolated systems, but evolving structures assembled slowly through gravity, interaction, and time across the history of the universe. As the inner regions of the galaxy continue their slow rotation beneath vast concentrations of ancient starlight, the bulge and its surrounding globular clusters remain among the oldest surviving structures in the Milky Way. Long before Earth formed from the remnants of earlier stars, these populations were already orbiting through the young galaxy beneath skies untouched by planets, oceans, or life. Their stars have continued shining across nearly the entire age of cosmic history, enduring while spiral arms shifted, molecular clouds collapsed, and countless younger stars briefly appeared and vanished within the galactic disk. In their immense age and crowded brilliance, the ancient clusters and luminous bulge preserve a calm continuity stretching backward toward the earliest eras of galactic formation, when the Milky Way itself was still gathering from primordial matter drifting through the expanding universe. Deep within the crowded stellar background of the inner Milky Way, countless faint red dwarfs also orbit unseen among the brighter giants and supergiants dominating the visible glow. These small stars burn fuel so slowly that many will survive for trillions of years, far longer than the current age of the universe. Although individually dim, their enormous numbers contribute substantially to the total stellar population near the galactic center. Around some of them may circle ancient planetary systems formed billions of years before Earth existed. Any night sky seen from such worlds would be filled with dense rivers of starlight crossing every horizon, while the central bulge of the galaxy blazed overhead with a brilliance unknown within the quieter outer disk. Yet even there, beneath skies crowded by innumerable suns, vast distances would still separate most stars from one another. The inner galaxy may appear overwhelmingly full compared to the solar neighborhood, but space itself remains dominant, preserving immense oceans of darkness between the ancient stars orbiting endlessly around the hidden heart of the Milky Way. Across these central regions, gravity continues shaping stellar motions, guiding clusters, dust, gas, and suns through repeating paths that will persist long after the spiral arms have shifted into new forms beneath the rotation of the galaxy and the passage of cosmic time. Beyond the crowded stellar heart of the Milky Way, hidden beneath layers of dust, radiation, and ancient starlight, there exists an object so compact and so powerful that it quietly governs the motions of stars across the innermost regions of our galaxy. At the exact center of the Milky Way lies a radio source known as Sagittarius A*, often abbreviated as Sagittarius A star. For decades, astronomers suspected that something extraordinary occupied this location. The stars nearest the galactic center were moving far too quickly to be explained by visible matter alone. Careful observations revealed stars racing around an apparently empty point in space at thousands of kilometers per second. Only an immense concentration of mass could produce such motions. By tracking the complete orbits of these stars over many years, astronomers eventually reached a remarkable conclusion. Roughly 4 million times the mass of our Sun is compressed into a region smaller than our solar system. The simplest explanation, and the one supported by overwhelming evidence, is that Sagittarius A* is a supermassive black hole. Unlike the black holes formed by collapsing stars, Sagittarius A* belongs to an entirely different class of object. Stellar black holes typically contain a few times the mass of the Sun. Sagittarius A*, by contrast, contains millions of solar masses. Similar supermassive black holes appear to exist at the centers of most large galaxies throughout the universe, suggesting that they play a fundamental role in galactic evolution. Despite its enormous mass, Sagittarius A* is surprisingly quiet compared to the giant black holes found in some distant galaxies. In active galaxies, central black holes consume large quantities of gas and dust, producing brilliant jets and radiation visible across billions of light-years. Sagittarius A* currently exists in a relatively calm state. It still accretes matter, but only slowly, emitting far less energy than many of its more active cousins. If a spacecraft could somehow approach Sagittarius A* safely, it would not encounter a giant cosmic vacuum cleaner pulling everything inward. At large distances, the black hole's gravity behaves exactly like the gravity of any other object with the same mass. The Sun could theoretically be replaced by a black hole of equal mass, and Earth would continue orbiting almost unchanged. What makes black holes unique is not their gravity at great distances, but the extreme concentration of mass within a tiny region. The boundary surrounding a black hole is called the event horizon. Once anything crosses this boundary, no signal can escape back into the universe. Not even light can travel outward. For Sagittarius A*, the event horizon is surprisingly modest compared to the scale of the galaxy, spanning only a tiny fraction of a light-year despite containing millions of solar masses. The existence of Sagittarius A* was confirmed through decades of patient measurement. Astronomers observed individual stars orbiting the invisible center, tracing complete elliptical paths. One star in particular, known as S2, completes an orbit in only about 16 years. Its motion provided some of the strongest evidence ever collected for the presence of a supermassive black hole. Near Sagittarius A*, gravity becomes so intense that Einstein's theory of general relativity must be used to describe motion accurately. Space and time themselves become distorted. Clocks closer to the black hole run more slowly relative to distant observers. Light changes energy as it climbs out of the deep gravitational well. The very geometry of space-time bends beneath the concentration of mass. Although black holes are often imagined as cosmic destroyers, Sagittarius A* has likely coexisted with the Milky Way for billions of years. The stars of the bulge continue orbiting peacefully around the galactic center. Entire generations of stars have formed, evolved, and died while the central black hole remained hidden within the nucleus, exerting its influence quietly across the ages. In 2022, astronomers revealed the first direct image of Sagittarius A star. The image was not a traditional photograph but a reconstruction created using radio telescopes spread across Earth. Together, these instruments formed a virtual telescope nearly the size of the planet. The resulting image showed a glowing ring of hot material surrounding the dark shadow cast by the black hole. Yet even Sagittarius A* is not the largest structure associated with our galaxy. Far beyond the visible stars, beyond the spiral arms and the glowing bulge, the Milky Way is enveloped by something far more mysterious. The visible galaxy represents only a fraction of the Milky Way's total mass. When astronomers measure how stars orbit within galaxies, they find a puzzling discrepancy. The visible matter, stars, gas, dust, planets, and nebulae, does not provide enough gravity to explain the observed motions. Galaxies should rotate more slowly than they do. Instead, stars far from galactic centers move unexpectedly fast. According to the visible mass alone, many of them should escape into intergalactic space. Yet they remain gravitationally bound. Something unseen appears to be providing additional gravity. This invisible component is known as dark matter. Dark matter does not emit visible light. It does not reflect light. It does not appear to absorb light in any significant way. Its presence is inferred almost entirely through gravity. Though invisible, dark matter appears to dominate the mass budget of the Milky Way. Current estimates suggest that most of the galaxy's mass resides not in stars but in an enormous dark matter halo surrounding the visible disk. This halo extends far beyond the familiar spiral structure. While the bright portion of the Milky Way spans roughly 100,000 light-years, the dark matter halo may stretch several 100,000 light-years into space. If human eyes could somehow perceive dark matter directly, the Milky Way would appear vastly larger than it does today. The familiar spiral galaxy would occupy only the central region of an immense spherical cloud extending deep into the surrounding darkness. The exact nature of dark matter remains unknown. It is one of the greatest unsolved problems in modern physics. Numerous candidates have been proposed, ranging from exotic particles to entirely new forms of matter not yet detected in laboratories. Despite decades of research, no definitive answer has emerged. Yet the evidence for dark matter continues to accumulate. Observations of galaxy clusters, gravitational lensing, cosmic structure formation, and galactic rotation all point toward the existence of a large invisible component shaping the universe. The Milky Way's dark matter halo acts as a vast gravitational framework. Within this framework, ordinary matter gathered over billions of years, eventually forming stars, planets, and spiral arms. In many ways, the visible galaxy may be viewed as a luminous decoration embedded within a much larger invisible structure. The halo also contains ancient stars, globular clusters, and streams of stellar debris left behind by smaller galaxies absorbed during the Milky Way's growth. These streams trace long arcs across space, preserving records of ancient mergers that occurred billions of years ago. The Milky Way did not emerge fully formed. Like many galaxies, it grew gradually by accreting smaller companions. Throughout cosmic history, gravity drew neighboring dwarf galaxies inward. Some were stretched apart and absorbed entirely, contributing stars to the growing halo. Even today, this process continues. One of the most famous neighboring systems is the Large Magellanic Cloud. Visible from the southern hemisphere as a faint luminous patch in the sky, it is actually a separate dwarf galaxy orbiting the Milky Way. The Large Magellanic Cloud contains billions of stars. Though much smaller than the Milky Way, it possesses its own star-forming regions, star clusters, and complex internal structure. It is not merely a cloud but an entire galaxy in its own right. Nearby lies its companion, the Small Magellanic Cloud. This second dwarf galaxy also orbits the Milky Way and interacts gravitationally with both the Large Magellanic Cloud and our own galaxy. These galaxies are named after the Portuguese explorer Ferdinand Magellan because members of his expedition recorded them during their circumnavigation of Earth in the 16th century. Yet long before European exploration, indigenous peoples of the Southern Hemisphere had observed and incorporated these celestial companions into their own traditions and sky knowledge. The Large Magellanic Cloud contains one of the most spectacular star-forming regions in the local group of galaxies, the Tarantula Nebula. This immense stellar nursery is so luminous that if it were located as close to Earth as the Orion Nebula, it would cast visible shadows at night. Within the Tarantula Nebula, massive stars form in extraordinary numbers. Radiation, stellar winds, and supernova explosions sculpt enormous cavities in the surrounding gas. It serves as a natural laboratory for studying star formation under extreme conditions. The Magellanic Clouds are connected by streams of gas pulled outward through gravitational interactions. These structures reveal the continuing dance between neighboring galaxies. Gravity stretches and reshapes them over millions of years, creating bridges and streams that span vast distances. One particularly remarkable structure is the Magellanic Stream, a ribbon of gas extending across much of the sky. This stream trails behind the Magellanic Clouds as they orbit the Milky Way, providing evidence of their long gravitational history. Astronomers now believe that the Magellanic Clouds may be making one of their first close passages around the Milky Way rather than having orbited repeatedly for billions of years. Ongoing observations continue refining our understanding of their motions. The Milky Way possesses many other satellite galaxies as well. Some are so faint that they remained undiscovered until recently. These dwarf galaxies contain relatively few stars compared to the Milky Way, but provide valuable clues about galaxy formation and dark matter. Several of these satellites appear highly dominated by dark matter. Their stars move in ways suggesting that invisible mass far outweighs visible matter. As a result, dwarf galaxies have become important targets in the search for understanding dark matter itself. Far beyond the Magellanic Clouds lies the broader environment of the local group, a collection of more than 50 galaxies bound together by gravity. The Milky Way and the Andromeda Galaxy are the two largest members. The Andromeda Galaxy resides roughly 2.5 million light-years away. Even at the speed of light, a journey there would require millions of years. Yet on galactic scales, Andromeda is considered a close neighbor. Measurements reveal that Andromeda and the Milky Way are moving toward one another. Several billion years from now, the two galaxies will begin a slow gravitational encounter. Contrary to popular imagination, this future collision will not resemble cars crashing together. Because stars are separated by such enormous distances, direct stellar collisions will remain extremely unlikely. Instead, the galaxies will gradually pass through one another, their structures distorted by gravity. Over billions of years, spiral arms will stretch and reshape. Gas clouds will compress. New waves of star formation may ignite. Eventually, the two galaxies will merge into a larger system. Long before that distant future arrives, however, the Milky Way will continue its quiet rotation through space. Stars will orbit the center. Molecular clouds will collapse. New suns will ignite while older stars fade. From the perspective of a human lifetime, the galaxy appears unchanging. Yet every component remains in motion. The spiral arms evolve. The halo grows through accretion. Satellite galaxies drift through the darkness. Even Sagittarius A asterisk slowly consumes matter at the heart of it all. And now, as our journey approaches its end, we drift outward once more. Imagine traveling beyond the outermost spiral arms, beyond the regions where star formation actively illuminates the galactic disk, beyond the halo stars and the ancient globular clusters, beyond the invisible reaches of the dark matter envelope itself. The Milky Way begins to shrink behind you. At first, the galaxy still dominates the sky. Its spiral arms curve outward in pale rivers of light. The central bulge glows softly at its heart. Dust lanes trace dark patterns across its disk. Hundreds of billions of stars merge into a single luminous structure suspended against the blackness. Continue farther. The galaxy becomes smaller. The Orion Arm, home of the Sun, vanishes into the larger pattern. Individual nebulae disappear. Star clusters become indistinguishable from the surrounding glow. Distances that once seemed unimaginably large collapse into details too small to see. Farther still, the Milky Way now appears as a complete galaxy, a rotating island of light. A vast stellar city floating alone in darkness. The sun, earth, every mountain, every ocean, every living thing that has ever existed occupies a location so tiny within that structure that it can no longer be identified. The galaxy continues to recede. Around it stretches the intergalactic void. Contrary to many artistic depictions, this void is not crowded with stars. It is overwhelmingly empty. Between galaxies lie distances measured not in thousands of light-years, but in millions. Here, darkness becomes deeper than anything experienced within the galactic disk. Yet even this emptiness is part of a larger cosmic web connecting galaxies across the observable universe. The Milky Way is not isolated. It belongs to the local group. The local group belongs to larger structures. Those structures belong to even greater arrangements spanning hundreds of millions of light-years. The universe extends outward on scales almost beyond comprehension. And still, our home remains the Milky Way. A galaxy shaped by gravity. A galaxy filled with ancient stars. A galaxy where molecular clouds quietly create new suns. A galaxy surrounded by invisible dark matter. A galaxy accompanied by smaller companions drifting through the halo. A galaxy whose center contains a supermassive black hole hidden behind curtains of dust and light. For billions of years it has turned slowly through the darkness. For billions more, it will continue. And somewhere within one small spiral arm, orbiting an ordinary yellow star, a tiny planet circles quietly through space. On that planet, for a brief moment in cosmic history, living beings learned to look upward. They learned that the stars were suns. They learned that the Milky Way was a galaxy. They learned that galaxies fill the universe. And they began, little by little, to understand where they are. As our journey comes to rest at the edge of our galactic home, allow the immense scale of it all to settle gently into the background. The crowded bulge, the glowing spiral arms, the dark halo, the ancient clusters, the neighboring galaxies, and the hidden black hole at the center all become parts of a single quiet picture. The Milky Way is vast beyond ordinary imagination. Yet it is also home. A place where atoms forged in ancient stars gathered together, became planets, oceans, living creatures, and eventually curious minds capable of contemplating the galaxy itself. Now the galaxy drifts peacefully beneath us. The stars continue their ancient motions. The dark matter halo remains invisible. The satellite galaxies follow their long orbits. The core shines softly from afar, and the intergalactic darkness stretches endlessly beyond. There is nowhere else you need to travel tonight. No distance left to cross. No mystery you must solve before resting. The galaxy will continue its journey whether we watch it or not. The stars will continue shining. The clouds will continue collapsing into future suns. The universe will continue unfolding across timescales far longer than any human life. For now, simply imagine the Milky Way suspended in silence. A luminous island in a cosmic ocean. Calm, ancient, endlessly patient. And as the great galaxy slowly turns beneath the darkness, may your thoughts become lighter, your breathing slower, and your rest as peaceful as the quiet stars drifting through the vast and timeless night.